Welcome to our presentation on system estimation and multi-equation models. Today, we'll explore why looking at the bigger picture in econometrics is crucial. As illustrated in the central diagram, economic phenomena like macroeconomic factors, firm performance, and market dynamics are not isolated. They exhibit causality, feedback, and simultaneous influence. We will cover the theory, practical implementation in EViews, and analysis of these powerful techniques. The core idea, inspired by Aristotle, is that by estimating equations together as a system, we gain more information than by looking at each part in isolation. The whole is indeed greater than the sum of its parts. Imagine trying to understand a car engine by only studying the spark plug. You miss how it interacts with the piston and fuel injector. System estimation is like studying the entire engine running together. So why can't we just use our standard single equation methods? Let's delve into the fundamental problem that system estimation solves. The slide illustrates the fundamental problem of interdependence in economics, where variables like investment and GDP are interconnected, influenced by factors such as consumption and interest rates. Unlike the assumption of independent variables made by ordinary least squares, or OLS, economic variables often exhibit complex feedback loops and simultaneous relationships. For example, investment influences GDP, and a higher GDP can then stimulate further investment. This creates a situation of simultaneity and correlation, indicated by the error terms U1 and U2 in the diagram. A key limitation of single equation models like OLS is their inability to capture these interdependencies and cross-equation error correlations, leading to potential inefficiencies and biases. The solution is joint estimation, or system estimation, which addresses these issues. This approach offers several key advantages. It increases efficiency by providing lower standard errors, as seen in methods like SIR, ensures consistency by fixing endogeneity bias with methods like 3-cell SLS or FIML, and facilitates testing of theoretical restrictions across different equations, such as symmetry. This flowchart guides us in selecting the appropriate estimator for multi-equation models. We begin by asking if our equations share parameters or have correlated inners. If not, simple OLS, ordinary least squares, applied equation by equation is sufficient. If they do, the next critical question is whether endogeneity exists. If there is no endogeneity, but the errors across equations are correlated, then seemingly unrelated regression, or SIR, is the efficient choice. If endogeneity does exist, we then ask if we have valid instrumental variables. If the answer is yes, then three-stage least squares, or 3SLS, or the generalized method of moments, GMM, are the appropriate methods. GMM is generally preferred if heteroscedasticity is present. If we have endogeneity but no instruments, full information maximum likelihood, FIML, might be an option, though it requires strong distributional assumptions. This table provides a concise summary. OLS handles neither endogeneity nor error correlation. It's a simple baseline. SUR is a step up. It doesn't handle endogeneity, but it efficiently estimates systems with correlated errors, like demand systems. 2SLS, or two-stage least squares, is a single equation method that handles endogeneity but ignores cross-equation error correlation. 3SLS combines the strengths of SUR and 2SLS. It handles both endogeneity and error correlation, making it ideal for simultaneous macroeconomic models. GMM and FIML are the most advanced. They both handle endogeneity and error correlation. GMM is robust to heteroscedasticity and non-normality, while FIML is efficient for small samples but requires specific distributional assumptions. If you're building a large macro model of an economy where inflation, unemployment, and interest rates all affect each other, 3SLS would be a strong candidate because it tackles both the simultaneity, endogeneity, and the correlated shocks across markets. Behind these methods lies a unifying mathematical framework. Let's look at the intuition of how system estimation works. Pro tip: if you are unsure about the error distribution, normality, GMM is often the safest bet for systems, provided you have a sufficiently large sample size. At its core, system estimation works by stacking all the individual equations into one large model. Here, y is a vector containing all the dependent variables from all equations, and x is a large block diagonal matrix of the regressors. The estimation is then performed using GLS, or generalized least squares. The formula looks similar to OLS, but with a crucial addition, the weighting matrix, omega. This matrix omega contains information about the variances and covariances of the error terms. For OLS, omega is simply an identity matrix, meaning we assume no correlation and constant variance. For SUR, omega is the estimated covariance matrix of the residuals, which allows us to give more weight to equations with smaller error variance, thus increasing efficiency. Think of omega as a reliability matrix. If one equation in your system has very noisy, unpredictable errors, high variance, the GLS estimator will automatically pay less attention to it when calculating the coefficients, leading to a more precise overall result. This is the theory. Now, let's see how to put this into practice by creating our first system object in EViews. To begin in EViews, you need to create a system object. The standard way is to navigate through the menu, Object, then New Object, and select System from the list. A faster way, especially if your variables are already organized, is to highlight the group of variables you need in the work file, right-click, and choose Open as System. EViews will then create the object for you. Once the system object is open, you can type your equations. The syntax is straightforward. For example, consumption equals C1 plus C2 times income. Here, C1 and C2 are the coefficients to be estimated. If you wanted to model consumption and investment, you would open a new system object and type two lines. Consumption equals C1 plus C2 times income, and investment equals C3 plus C4 times rate. EViews understands that this is a two-equation system. After creating the object, the next step is to correctly specify all the equations and, if necessary, the instrumental variables. Inside the System Object window, you'll write each equation of your model on a new line. You can see here a three-equation macro model for gap, inflow, inflation, and FF, federal funds rate. If you are using an instrumental variable method like 3SLS or GMM, you must declare your instruments. This is done using the @inst command, followed by a list of all instrumental variables. Crucially, this list must be placed at the very end of your system definition. It's best practice to manually assign coefficient names, like C1, C2, and so on. While EViews can assign them automatically, manual assignment gives you full control, which is essential for imposing restrictions and interpreting structural models later on. In the example shown, GDP_lag and gov spending are used as instruments for the endogenous variables gap and inflow that appear as regressors in the system. The @inst command tells EViews to use these external variables in the first stage of the estimation. In the System Estimation dialog box, the first tab lets you choose your estimation method from a drop-down list, such as SUR, 3SLS, or Full Information Maximum Likelihood, as shown here. A crucial but often overlooked setting is under the Options tab. You should check the box for Iterate to Convergence. Why is this important? Without it, the results can be sensitive to the order of your equations. Iterating to convergence ensures that the estimator finds a stable solution, making your results robust and independent of the equation ordering. This slide presents a case study of a translog cost function, which is a common application for system estimation. Here, we see two equations for the cost shares of capital, SK, and labor, SL. Each equation includes terms for the prices of capital, PK, and labor, PL, often in logarithmic form. Economic theory, specifically the theory of production, imposes a crucial restriction on these models, the symmetry constraint. This constraint requires that the coefficient beta KL from the first equation must be equal to beta LK from the second equation. The question, why system, directly addresses this. We must estimate both equations simultaneously to force these coefficients to be identical. If we were to estimate them separately, there would be no mechanism to ensure this theoretical symmetry holds. On the right, under real-world use, we see that system estimation is a standard practice in several areas. First, for demand systems, such as AIDS, almost ideal demand system models. Second, for cost functions, as illustrated in this example. And third, for large-scale macro simulations, like Klein models, where many economic variables interact simultaneously. EViews makes imposing restrictions incredibly simple through a method called hard constraints. To enforce the symmetry constraint from our previous example, where the effect of the price of labor on the cost share of capital must equal the effect of the price of capital on the cost share of labor, you simply use the same coefficient name in both equations. In this EViews code, both coefficients are named C3. By assigning the same name, you are telling EViews that these are not two separate parameters, but one and the same. EViews will estimate a single value for C3 that best fits both equations simultaneously. This is a powerful way to embed economic theory directly into your econometric model. An alternative is a soft constraint, where you estimate freely with different coefficients, e.g. C3 and C5, and then use a walled test to check if they are statistically equal after the estimation. Look at the code. Share K equals C3 times log PL, and share L equals C3 times log PK. By using C3 in both places, we have forced the cross-price effect to be identical, directly implementing the symmetry condition. After we've estimated our system, whether restricted or unrestricted, the next step is to interpret the output. When you look at the output for a system estimation, you won't find a single R-squared value like in OLS. Instead, you need to look at system-wide goodness of fit measures. Two key statistics are the system's log likelihood and the determinant of the residual covariance matrix. The goal is to find a model that maximizes the log likelihood, or, equivalently, minimizes the determinant of the residual covariance. A smaller determinant implies that the model's errors are smaller overall, indicating a tighter fit for the system as a whole. You can use this to compare different specifications of your system model. For example, in the output for the currency system, the determinant residual covariance is 0.0095356. After estimation, you should always check the quality of your model. A key diagnostic is to test if the residuals are white noise, meaning they are not serially correlated. Portmanteau tests are commonly used for this. A crucial check before even using SUR is to confirm that the cross-equation correlations are significant. If the off-diagonal elements in the residual correlation matrix are close to zero, there's no efficiency gain from using SUR over simple OLS. You would be adding complexity for no reason. System estimation also makes it easy to test hypotheses across equations. The wall test can be used to test complex restrictions, such as whether coefficients in different equations are equal, like K1 equals J1, as shown in the dialog box. SUR, or seemingly unrelated regression, fails when you have simultaneity. This occurs when a dependent variable from one equation, say y2, appears as a regressor in another equation for y1, making y2 correlated with the error term of the first equation. This causes endogeneity and renders SUR inconsistent. The solution is 3SLS, or three-stage least squares, which requires instrumental variables to address this issue. However, 3SLS comes with a significant trade-off. It is powerful, but fragile. If even one equation is misspecified, it can contaminate the estimates of all other equations in the system, even the correctly specified ones. System GMM, or Generalized Method of Moments, is a powerful estimator that offers several advantages. First, it can handle heteroscedasticity and autocorrelation of an unknown form, which is very common in time series data. EViews allows you to specify HAC, or heteroscedasticity and autocorrelation consistent, covariance matrices for this within the system object, which is crucial for time series systems. Second, unlike maximum likelihood methods, GMM does not require assuming a specific distribution for the error terms, such as the normal distribution. This makes it more robust. Finally, GMM provides a built-in specification test, the J statistic. This tests the validity of your instruments, an over-identification test. In the output shown, the J statistic is 12.45890 with a p-value of 0.0142. If the p-value is high, you fail to reject the null hypothesis that your instruments are valid, which is a good result. For example, at a 1% significance level, this p-value is greater than 0.01, so we would not reject the validity of our instruments. However, at a 5% level, we would reject it. This highlights the importance of interpreting the J-stat in the context of your chosen significance level. A common and effective workflow for building structural models is to start with a VAR, or vector autoregression model. A VAR is a simple system where every variable is regressed on lags of itself and all other variables. It's great for capturing the general dynamic interactions in your data without imposing much structure. However, VAR models are often over-parametrized. The next step is to convert the estimated VAR object into a system object, which EViews can do with a single click. Proc, make system. Once you have the system, you have flexibility. You can then prune the model by removing statistically insignificant coefficients or impose theoretical restrictions. This process transforms the unrestricted VAR into a more interpretable and parsimonious structural model. Let's summarize some best practices for system estimation. First, always start simple by running OLS on individual equations to check your data quality and get a baseline understanding. Second, check the residual correlations. If the errors from your single equation models are not significantly correlated, there's little to no benefit in using SUR or other system estimators, as you'd just be adding complexity without value. Third, be mindful of your degrees of freedom. System models, especially VARs, estimate many parameters and can quickly exhaust your data, particularly with small sample sizes. Fourth, leverage the power of constraints in EViews. Use shared coefficients, such as CK, to impose theoretical consistency, such as homogeneity or symmetry. This integrates economic theory into your model, leading to more precise and meaningful estimates. Finally, a key takeaway. System estimation is fundamentally about leveraging information. The more you are able to tell your model about the underlying relationships, whether through explicit restrictions or by accounting for correlations across equations, the sharper and more efficient your parameter estimates will become. Thank you for joining this presentation on system estimation and multi-equation models. We covered the theory, practical implementation in EViews, and best practices for these powerful techniques. If you have any further questions, you can find more resources on our website at https://